Everyone thinks the AI race is going to be won by whoever builds the biggest, most expensive data center in the desert.
Right, that is the consensus.
But the data points to a completely different and, frankly, more dangerous reality. And if that is true, then the entire concept of an AI hardware moat is basically an illusion.
Yeah, the assumption is that the future is being built behind this massive wall of compute.
Exactly. And unless you have endless capital to burn, billions of dollars, you are permanently locked out.
It creates a massive bottleneck for innovation. I mean, training a foundational model today requires prohibitive costs, colossal data sets, and an almost monopolistic concentration of power.
And that bottleneck is exactly what we are doing a deep dive into today. Because if you are a specialized researcher or a startup founder, you just do not have the resources to build a world-class AI from the ground up.
You don't. But what if you didn't have to?
Right. So our mission today is to explore a 2025 review paper called Democratizing AI Through Model Fusion. And the core premise is, well, it's wild. It suggests that model fusion might be the ultimate hack to bypass these billion-dollar supercomputers.
Yeah, taking existing specialized models and somehow combining them into a single unified system.
So by the end of this, the important question is not who trains the biggest model. It is who can adapt fast enough to use the models we already have.
We are going to look at the evolution of this, starting with the early kind of brute force methods of literally mashing algorithms together.
All right, the Frankenstein approach.
Exactly. And then we'll explore why that hit a brick wall and how the field pivoted to cutting-edge techniques where we stopped touching the hardware entirely.
Okay, so let's unpack this, because looking at the source material, that early approach feels a bit like mad science.
It really was.
The paper calls it parameter-level merging. From my understanding, this is where researchers are actually getting under the hood and tweaking the internal weights of the models. But how does that actually work in practice?
Well, you are essentially taking the actual mathematical weights, the billions of numbers that define what a specific model has learned, and trying to combine them mathematically.
Just averaging them out.
Basically. The review highlights a few clever methods that attempted to do this gracefully. One of the primary ones is called ties merging.
I saw that mentioned. And it specifically talked about fixing interference. How exactly does it do that?
Think about what happens if you just take two complex models and average their numbers together naively.
Okay.
Let's say we have two models evaluating text. Model A has learned a feature, say, identifying a specific grammatical pattern, and assigned it a positive weight of 0.5.
So it leans heavily toward it?
Right. But Model B learned the exact same feature and assigned it a negative weight of 0.3. It leans away from it.
Oh, I see. So if you just average them, you get a positive 0.1?
Exactly. You've basically watered down the conviction of both models. You end up with a fragile AI that doesn't really know what it's looking at.
So ties merging looks at that mathematical clash and forces a decision.
Yeah, it trims redundant parameter values and resolves those sign disagreements by electing a single dominant direction. It forces the merged model to pick a lane rather than canceling itself out to zero.
That makes sense. And the paper also brings up another method called DARE. How does that fit in?
DARE tackles a different part of the same problem. When you merge these massive matrices of numbers, the models tend to step on each other's toes mathematically.
Which leads to a loss of the specialized knowledge they originally had, right?
Precisely. So DARE uses scaling terms and a technique called dropout, which means randomly ignoring certain weights during the merge.
To strictly control how much each model contributes.
Yeah, it preserves the unique capabilities of the original models without overwhelming the new fused system.
But looking at the broader picture here, there is a massive elephant in the room with parameter-level merging.
The architectural bottleneck.
Right. The paper points out a fatal flaw. This entire concept of mashing weights together only works if you have what they call architectural homogeneity.
Meaning, every model you are trying to merge has to have the exact same underlying architecture.
And the exact same token vocabulary.
Right. And if we look at the reality of the AI ecosystem today, that is almost never the case.
We have incredibly diverse model families. Llama, Mistral, Quinn.
Each with entirely different structures, different numbers of neural layers, completely different ways of tokenizing human text.
So this is like trying to build a supercar by literally welding the engine of a Ferrari to the transmission of a Ford tractor.
That's a good way to put it.
If the parts don't perfectly align, the whole thing tears itself apart. If the models don't share the exact same structure, doesn't direct weight interpolation just result in destructive interference?
It absolutely does. The knowledge transfer stops dead in its tracks.
So you just get garbage output.
Total gibberish.
Yeah.
If you attempt to average the weights of a 7 billion parameter model with an 8 billion parameter model, or even two models of the same size with different internal wiring, it breaks.
The structural barrier proved to be so high that the research community realized we needed a completely new approach.
We had to stop trying to weld the physical parts together. The hardware-level merger was a dead end.
Okay, so welding the Ferrari engine to the tracker transmission resulted in an exploding car. So how did the researchers bypass the physical hardware entirely?
This is where we see a massive paradigm shift in the paper. We move away from the hardware parameter-level merging and focus instead on the behavior.
The behavior of the models.
Right. Through knowledge distillation, specifically a technique called logits-level fusion.
Wait, hold on. If we aren't merging their code or their weights, how are they actually combining?
What?
I'm struggling to picture how Model A learns anything from Model B if their architectures are completely walled off from each other.
Think of it like two master chefs who don't speak the same language. They can't share their written recipes because they can't read each other's handwriting.
Right, that's the parameter level barrier.
Exactly. But if they both taste a complex soup, and they each adjust the salt, the acidity, and the spice levels until they both nod in agreement.
They've shared their culinary knowledge through behavior.
Yes. They didn't need a shared language. They just needed to align their final output. In the AI world, that tasting and adjusting process relies on logits.
Let me break down what a logit actually is for you, because it is a brilliantly simple concept once you see it. When an AI generates a response, it doesn't just confidently spit out one single word, right?
No, it internally generates a probability score for every possible word in its entire dictionary.
So if the prompt is, the sky is, the AI might have a 95% probability for blue, a 4% probability for overcast, and a 0.001% probability for falling.
And those soft target distributions, that list of percentages, are the logits.
And those soft targets are a goldmine of information.
They really are. They don't just give us the final, most likely answer. They capture the model's internal uncertainty.
It's nuanced understanding of how concepts relate in that context.
Right. So in logits-level fusion, researchers introduce a pivot model. This pivot model's entire job is to learn from the soft target distributions of multiple different source models.
It's treating the output behavior as a universal translator.
Exactly. It completely ceases to matter if the source models are built entirely differently on the inside.
Because on the outside, they're all just projecting these lists of probabilities.
And the breakthrough framework the paper highlights for making this happen is called InfiFusion.
InfiFusion, how does it actually force that alignment?
It formulates this behavioral alignment as a distribution-level optimization. The paper mentions it uses an optimal transport-based loss.
Okay, optimal transport loss. That sounds terrifying for anyone who didn't major in advanced statistics. What does that actually mean computationally?
Let's translate that into the Earth mover's distance.
Okay.
Imagine Model A's probability distribution is a pile of dirt located on one side of a yard, and the pivot model's current distribution is a pile of dirt on the other side.
Got it.
The optimal transport loss is basically a mathematical formula, calculating the most efficient way to shovel the dirt from the pivot model's pile so that it perfectly matches the shape and location of Model A's pile.
So it's literally just moving the probabilities around until they align perfectly.
Right, and the mechanics of InfiFusion rely on two really specific mechanisms to make that dirt shoveling efficient.
The first being top K logit selection.
Exactly.
From what I read, instead of looking at the probability of every single word in the dictionary, which would take forever, it only looks at the top most confident predictions.
That filtering is crucial. If Model A says there's a 0.0001% chance the next word after the sky is banana.
A pivot model doesn't need to waste compute power learning that useless data point.
Right. By focusing only on the top case, say, the top 10 or 20 most likely words, it filters out the low probability noise and focuses the learning entirely on the strongest signals.
And the second mechanism is logit standardization. Why is that necessary?
Because different architectures are inherently going to scale their probabilities differently.
Oh.
A highly confident model might give blue a 99% score, while a more cautious model might give it an 80% score, even if they both strongly believe it's the right answer.
So InfiFusion normalizes all the predictions to a zero mean and unit variance.
Yes.
So it's essentially grading on a curve, so all the models are on the same 1 to 10 scale.
That is the perfect way to look at it. It ensures that completely different models can actually compare notes on an apples-to-apples basis before the pivot model tries to learn from them.
And that sounds like a technical detail. It is not. We really need to talk about the numbers here because the efficiency gains are staggering.
The shift in capital required is massive.
Let's give you the exact stats from the 11 benchmarks they ran in the study. The InfiFusion framework achieved an average score of 79.92 across complex reasoning, math, and coding tasks.
Which is incredibly high.
But here is the critical part. It did this using only 160 GPU hours.
To really understand the magnitude of that, 160 GPU hours is roughly 35% of the compute used by older pairwise fusion methods.
But more importantly, it is an infinitesimal fraction of what it takes to build a model the traditional way.
Right. The paper notes it's just 0.016% of the compute required to train a full model like 5.4 from scratch.
And if you look at massive proprietary models, something like Mistral Small requires around 1.6 million GPU hours.
1.6 million compared to 160.
InfiFusion is getting comparable world-class performance for a fraction of a fraction of a fraction of the cost.
It represents a profound shift in power. You're taking specialized knowledge from heavyweights models that cost millions to train and distilling their collective intelligence into an incredibly lightweight, efficient pivot model that a small team can actually run.
But this is where the story gets uncomfortable, because this leads to a pretty major hurdle, doesn't it?
It does.
Okay, matching token probabilities is great if the task is simple. If the models all agree the next likely word is blue, the pivot model learns blue. But what happens during complex reasoning? What if the task isn't just knowing a solitary fact, but following a 10-step logical deduction where the relationships between the concepts matter far more than the individual words themselves?
That is exactly where standard token-level fusion hits a wall.
It just fails.
Completely.
Yeah.
If you only align individual tokens word by word, you're inherently ignoring the deeper causal chains that the model is forming during a complex task.
You missed the structure of the thought process.
It's like trying to learn how to build a house by only looking at the individual bricks rather than studying the architectural blueprint.
So how do you fix that bottleneck?
To solve this, the researchers introduced an evolution of the framework called InfiGFusion.
The G standing for graph, representing that structure. But what does a graph actually mean computationally here?
In computer science, a graph isn't a bar chart. It is a data structure made of nodes and edges.
Okay, nodes and edges.
The nodes represent the concepts or objects, and the edges represent the specific relationships between them. InfiFusion adds a structure-aware step.
So it doesn't just look at a linear string of text.
No, it maps out the web of concepts. It captures the causal chains across the entire sequence of thought.
The paper uses a really fantastic real-world example of this that shows exactly why that web of concepts is necessary.
The object tracking problem.
Yes, the condition-dependent object tracking problem. Imagine you are given a prompt that lists a bunch of items scattered on a floor.
Right.
It says, you see a green bracelet, a purple cat toy, a brown pair of sunglasses, a black fidget spinner, a red dog leash, and an orange pen. And then the prompt asks the model a tricky question. How many objects are neither black nor blue?
To a human, that sounds deceptively simple. But for an AI, it is highly error-prone.
Why is it so hard for them?
Standard models that just predict the next likely word often miss the negation entirely. They might drift from the rule midway through the list, or they accidentally double-count items because they lose track of the state of the room.
But because InfiFusion forces the pivot model to absorb the structured, graph-based reasoning of the source models, the result is completely different. How does it map that specific problem?
It creates nodes for every object, the bracelet, the toy, the spinner, and it creates edges that represent their color state and whether they meet the condition of the prompt.
So it forces the AI to meticulously analyze the list step by step.
Exactly. It evaluates the black fidget spinner, recognizes the black node, triggers the exclusion rule, and drops it. It scans for blue nodes, finds none.
It doesn't just guess a number.
No, it maintains the state of the logic across multiple steps and correctly counts the remaining 5 objects.
It's inheriting the structure of the reasoning, not just the vocabulary.
Right, and this structural awareness extends to abstract logic puzzles, too.
Like the Alice Bob Carroll paradox.
Yes, the classic truth-telling paradox.
Uh-huh.
The setup is, if Alice tells the truth, then Bob lies. Carroll says Bob is truthful. Who is telling the truth?
Standard models often hallucinate an answer here because they get tangled in the words.
But the InfiFusion model lays out the causal chain perfectly. It maps the contradictions, Carol saying Bob is truthful contradicts the rule about Alice.
So it deduces Alice lies, Bob tells the truth, and Carol lies. Therefore, only Bob is truthful.
It's a massive leap forward in making AI genuinely capable of multi-step deduction.
But as the review points out, getting an AI to reason correctly is really only part of the modern battle.
Oh, absolutely. The final stage of AI development is about ensuring the model behaves in a way that humans actually find helpful, safe, and appropriate.
And this brings us to preference alignment, or PA. For you listening, if you've heard the term RLHF reinforcement, learning from human feedback, this is what we're talking about.
Right.
I like to think of it as sending the AI to etiquette school. It's where models learn that they shouldn't just output raw, unfiltered, or potentially toxic data, but rather output information in a format, tone, and structure that aligns with human values.
And historically, model fusion completely ignored this etiquette school stage.
It was just skipped entirely.
Prior methods were entirely focused on the supervised fine-tuning stage, just getting the facts and the logic right. But there's a massive danger there.
Right, because if you merge models without merging their preference alignments,
You get an AI that might be incredibly smart, but acts completely erratically or inappropriately when interacting with a human user.
So to fix this, the researchers introduced InfiFPO, implicit model fusion via preference optimization.
Yeah.
If logit fusion is teaching the models to speak the same language, InfiFPO is teaching them to share the same manners and cultural norms.
Exactly.
But here is where I need you to clarify something. The paper emphasizes that InfiFPO operates at the sequence level rather than the token level. Why does that distinction matter so much?
It comes back to the vocabulary mismatch problem we talked about earlier. Let's say you try to align the human preferences token by token, word by word.
Okay.
You run into the issue where Model A's internal dictionary represents the word apple with token number 45, but Model B represents the word the with token number 45.
Oh, wow. So they completely disagree on what the number means.
Right. So if you optimized at the token level, the human preference signals get completely scrambled. Model A thinks token 45 is a safe fruit. Model B thinks token 45 is just a grammatical article.
So the feedback is basically applied to the wrong concepts.
Precisely. By operating at the sequence level, meaning the algorithm looks at the entire generated sentence, paragraph, or response as a single holistic unit. InfiFPO completely sidesteps the vocabulary mismatch.
It's evaluating the entire thought for its etiquette rather than spell-checking individual letters.
That is exactly what it's doing.
That is wild. It means the pivot model can assimilate coherent reasoning patterns and human-aligned values from completely different source models like Quinn, Mistral, and Gemma all at the same time.
It just absorbs their manners organically without the underlying architectures clashing.
And the performance data backs this up beautifully. InfiFPO showed consistent improvements across safety and helpfulness benchmarks.
It also notably jumped nearly 5% in mathematical reasoning and almost 6% in code generation compared to the base models.
And importantly, it scales cleanly, right?
Yeah, as you add more source models to the fusion process, the pivot model continues to refine its preferences without degrading.
Okay, we've covered a lot of ground today. We've talked about Earth movers distances, grading on a curve, nodes and edges, and sequence-level optimization.
A lot of technical mechanics.
Right. But if you are a developer listening to this, or just someone tracking where the AI industry is heading in the next 12 to 36 months, what does this actually mean for you? Why do these algorithmic gymnastics matter outside the lab?
It all comes back to that fortress we talked about in the very first minute, the multi-billion-dollar supercomputers.
And Moat.
The Moat. For a long time, the organizational adaptation required to deploy state-of-the-art AI was restricted to massive tech companies. Model fusion is the sledgehammer breaking down the walls of that fortress.
By drastically lowering the hardware bottlenecks, we are handing the power of world-class custom AI back to domain experts.
And the paper provides incredible specific evidence for this in the medical field, which I think is the perfect proving ground.
They detail a series of models called InfiMed.
The medical field is the ultimate test case because it is notoriously data scarce and highly specialized. You can't just scrape the open internet to teach a model how to interpret a complex 3D radiology scan or diagnose a rare pathology.
The data is siloed and protected.
Exactly. So what the researchers did was use data-level model fusion. They used massive, generalized source models as data generators to transfer deep clinical expertise into a specialized pivot model.
And the resulting InfiMed models are tiny by modern standards, just 3 billion parameters.
But because of the fusion techniques, because they perfectly inherited the logic graphs and the preference alignments of much larger models, those 3 billion parameter InfiMed models are actually beating massive general proprietary models on specialized medical multimodal benchmarks.
They are outperforming giants on tasks that require deep clinical understanding.
All while running on hardware that a local hospital or a university research lab could actually afford.
It's the ultimate David and Goliath story, powered by brilliant mathematics.
It really is.
To summarize the journey of this deep dive, we have moved from the brittle, hardware-dependent days of parameter merging, where you had to have identical architectures to even attempt a combination, to the flexible, behavior-driven world of logits and preference fusion.
Through frameworks like InfiFusion, InfiGFusion, and InfiFPO, researchers are decoupling the intelligence of an AI from its physical hardware.
Unlocking high-end, complex reasoning for the masses using a fraction of the computing power.
Which leaves us with a rather profound philosophical question to consider.
Yeah.
We've seen today that we can perfectly fuse the knowledge, the complex logical structures, and the human preferences of a dozen completely different AI models simply by aligning their external probabilistic behaviors.
Right, we never need to touch their internal architecture to extract their intelligence.
So if that is true, does the black box of an AI's internal brain even matter anymore? Or is artificial intelligence ultimately defined entirely by the behavior it projects to the outside world?
That is a heavy thought to leave on. If the behavior is perfectly aligned, maybe the internal architecture is just scaffolding. So here's the real question for you. What breaks first, the hardware moats of the major labs, the licensing models of proprietary data, the coordination of decentralized open source teams, or the trust in centralized AI entirely?
It's going to be a fascinating couple of years.
It is. Most people are watching the model leaderboard. The real leaderboard is deployment, infrastructure, and organizational adaptation. The future will not arrive evenly. It will arrive wherever intelligence has the fewest bottlenecks.